Welcome to our new webinar. My name is Gabriele Meurer. I'm a regional sales manager at Yxlon, and I'd like to welcome you on behalf of the entire Yxlon team and the AM Group. This is the fifth webinar in our series on quality assurance and process optimization in additive manufacturing and on the role of computer tomography. The presentation will take approximately 30 minutes, and afterwards we will have a Q&A session. If you have a question, please write it in the Q&A section. We will discuss the questions at the end of the presentation and answer them live in the webinar. For data protection reasons, no names will be published. But if there are any questions that we cannot answer live during the webinar, we will answer the questions afterwards via email. Now on to today's topic. Our guest today is the HAIDLMAIR company. HAIDLMAIR is a machine tool manufacturer and the global market leader in mold making for bottle crates and storage and logistics containers. They use additive manufacturing to produce and optimize tools and molds for injection molding, which is a mass technology. This requires a high degree of accuracy to ensure durability, availability, and high cycle times of the molds. Industrial computer tomography is used for testing in order to see, for example, if and how the different materials connect and if additive structures have any defects. And this, in turn, provides information about the printing process. And it's also an interesting fact that HAIDLMAIR has been climate neutral since this summer. And now I'd like to introduce today's speaker, Sara Furtner. She graduated from the University of Applied Sciences in Vienna, where she got her bachelor's degree in biomedical engineering. In her master's, she specialized on functional imaging and radiotherapy in medical technology. She's been with HAIDLMAIR since 2020 as an application specialist and is responsible for tests with computer tomography. And now, Sara Furtner, the floor is yours. Thank you, Mrs. Meurer, for the kind introduction. Before I start my presentation, I'd like to tell you a bit about our company in general. HAIDLMAIR Group consists of 9 companies in 4 countries that include HSC, Digital Molds, Testify, and FDU Hot Runner. In the HAIDLMAIR Group as a whole, we had a turnover in the fiscal year 2020-2021 of 62.5 million euros. HAIDLMAIR GmbH contributed a share of 43 million euros to that. We're located in Grenztal in Nussbach in Austria, and in our headquarters we currently have a team of around 300 employees, which you can see on the picture. In the HAIDLMAIR Group, we have around 550 employees in 9 companies in 4 countries, as I said. As Mrs. Meurer already said, we are the global market leader in bottle crates, beverage crates, but apart from that, we also have many molds for transport boxes, foldable boxes and pallets. But we also have large molds, such as big boxes or garbage cans. The automotive industry and some other industries also have a minor share. Here you can see the closed loop of our company. As you can see, it all starts with our clients' ideas. Our clients approach us with a certain idea, and together with them we will then develop and optimize their ideas and products. When the product is optimized, the next step is advanced simulations. Here we can further optimize the product. We do that by simulating the injection molding process before even producing the product. The next step is prototyping, that's additive manufacturing. Here the client can hold their products in hand for the first time. With our plastic printer we can rapidly do the prototyping so that the clients can actually see what they will get. Once the component is designed by our CAD design team and the mold is finalized, it moves on to CAN programming, to production, and finally we also assemble it in our company. All of these steps are possible here in Nussbach. When the mold is finished, it is forwarded to our technikum. We have several injection molding machines and we approve every mold before we deliver them in order to ensure maximum quality. If the clients are satisfied with this, we move on to quality assurance. That is my field of expertise, industrial computer tomography. Here we can evaluate optical defects, we can detect cavities, do metrological measurements, everything that we can see in a CAD design can be tested with computer tomography. If the client is satisfied, we can then deliver the mold. At the bottom left, you can see two more symbols. That's digital molds on the one hand. This is one of our subsidiaries. They manufacture small electronic boxes which monitor the tool in operations. We can check KPIs such as cycle times and temperatures and mold temperatures in real time. And then there's also international service. This is our after-sales team. When the mold has been in operation for a certain amount of time, there is normal wear and tear, and we can take care of this with our international service for any queries that might arise after we deliver the molds. So now let's get started with the topics we want to discuss in today's presentation. Let's start with additive manufacturing and the plastic printers. We have two plastic printers in our companies. That's conventional FDM process printers, so those are plastic printers with a plastic wire which is melted and then printed in layers. We use the Fortis 900 MC and the Upprint SE Plus. Fortis 900 MC is a large printer with a build space of 900 by 900 by 600 millimeters. We can print different kinds of materials such as ASA or nylon in different shades and colors. And we also have many possibilities of different nozzles between T12 and T20 nozzles. And here you can also see the wall thicknesses and the accuracy. Also in the pictures you can see some examples that we printed, and you can see that there are many possibilities for small and large printed components. We also have a metal printer. The concept laser is a traditional powder-based process printer, so a selective laser sintering printer. There are many applications and we can print components of 250 by 250 by 350 millimeters. Different materials or material alloys are possible, and we can print up to 35 cubic centimeters per hour. Again, you can see several pictures of applications and examples that we print in our company. Now, those were the conventional 3D printers. I would now like to present our hybrid machine, the LaserTech TT. This machine combines a classic 5-axis milling machine with an additional laser head, so that's additive manufacturing. And this provides different advantages. So we can work in a cooling optimized and load optimized way, and different powders can be processed at the same time. And this not only saves time because you can work with two powders at the same time, but it's also possible to create alloys. The powders can be exchanged very quickly, and especially when compared to a conventional metal printer, this is an advantage because it is much faster. Also, we can work more quickly because we don't have to respan, and we can work selectively. We can also replace mold max. This is particularly interesting for mold making. And the components from Lasertec are completely finished, so no post-processing is required. That is because this is a layer-wired principle. So we always print, then we mill the contours and the edges, then again we print, and then we mill. And now I've told you a lot about additive manufacturing. We will now move on to the heart of our company. That's my field of expertise, the industrial computer tomography. We use a CT modular from Yxlon. This is a computer tomograph that can be used in many different areas, and this is one of the largest ones in Austria. We have a microfocus tube with an output of 250 kV for high precision measuring. We also have a mini focus tube. This is our power horse with up to 320 kV. We also have two different types of detectors in our CT. On the one hand, we have the digital flat panel detector, which is a state-of-the-art detector we use for horizontal and vertical measurements. And then we have a line detector. This is a very special detector. It is used for large components of a length of up to 1.20 meters, and it's so special because we can evaluate multi-material components with significantly less artifacts than with conventional methods. Computer tomography is a non-destructive testing method with which 100% of the component can be depicted in a watertight way without destructing it. And also multi-material testing is possible because no matter how many materials are used, they can be measured and detected as long as they have different densities. And the accuracy depends on the component size. For evaluation, we use the software VG Studio Max in the latest version. Now I'd like to point out some of the functionalities of the CT, which are important for understanding what I'm about to tell you. The X-ray source emits specific X-rays, and they are then measured by the detector. In the middle, the component stands on a turntable, and during the measurement, the turntable rotates, and many individual 2D X-ray images are taken from different angles. The computer can then reconstruct this into a three-dimensional volume. So we have the entire component. The denser the material, the more radiation is absorbed. In computer tomography, we always speak about voxels. And a voxel is a three-dimensional pixel, and each of these voxels has a certain gray value. The lighter the gray value, the less X-rays arrive there, reach that area, so that means that the material is denser. Now let me show you some applications of our Lasertec. As I said, it is possible to print two different types of materials simultaneously, and this makes it possible to create alloys. This can be done, for example, if we have a softer steel on the inside and a harder steel on the outside of a component. This is, for example, the case for turbine blades or in some gears and wheels. Here, for example, you can see a dual component with two different steel alloys with different hardnesses. This is one of our traditional applications. The lighter areas are the harder material, which is important for the durability of the mold. Also, we can print onto existing components. This is not just more cost effective and quicker because 3D printing takes some time, but it also brings along some other advantages. For example, we can reinforce selectively in certain areas. This is something that we do every day in our company. Here, for example, you can see a base plate, and on these complicated edges, a cooling optimized material was applied selectively to make sure that the material hardens more quickly. And this is another example. This is a before and after comparison. This is a repair that took place here. Of course, this is also possible. If you have an existing component, you can remove some material and then print new material on top of it, so you don't have to replace the entire part. Complicated repairs is also the next point I'd like to discuss. When you have different components where there is a lot of wear in a certain area, you can deliberately weld on harder materials here, or you can do the opposite. When the mating part is easy to repair, you can print softer material here to make sure that wear takes place here and not on the part where repairs are more difficult. You can see an example here. This is an injection nozzle, and all around the nozzle, where the part has to be very strong, a harder material was used, and all around it, the material that was printed has a high cooling coefficient because it's important that it cools down quickly. Also, specific cooling solutions can be done. We have this step-by-step process, as I said, with the laser tech, milling, printing. We can also realize specific cooling solutions. And now on to today's actual topic. What do we test with our computer tomographs? On the one hand, we can see whether or not the individual materials have bonded well. You can see a picture here. This is the sort of thing that I see on my desk every day. This is what a component looks like in the software. We have different views here from the top, from the right, and from the front. And at the bottom, you can see the surface of the component. And in the top right, you can see that the upper area is light, then in the middle it gets a little darker, and it gets lighter again at the bottom. And that's exactly what we wanted here, because two different kinds of materials were used here. You cannot see that on the component because the two materials have the same colors, but in the CT scan we can see that different material was used. Also, we can see very well here that the material has bonded well, so there are no abnormalities where the two different materials touch. Also, we can check whether or not welded seams are okay. In this example, you can see that there is a welded seam, and we can now optically test whether or not it is well done and will be tight or not. Then we can do a general defect and function analysis. There's an example here. I made this red cross here to highlight this dark spot. This dark spot is a cavity where there is air entrapped. And unfortunately here it is problematic because this is a critical form. There cannot be any cavities in this area, so it will have to be repaired. And obviously we cannot only do general function and defect analysis, but we can also look at cavities and cracks and the like. In this example, you can see a crack on the left. And this is a near contour area, so this crack is problematic. If it were elsewhere on the top here, for example, it would not be problematic, but as it is located in a function critical area, it will have to be repaired. This is another example of how we supply the results to our clients when we do a 100% test of a part. In these videos, you can see that the entire component is depicted 100%. On the right-hand side, you can see the videos from front to back, and on the right-hand side from the top down. And you can see these dark spots here, and these dark spots are cavities. And I have evaluated these cavities here. Here you can see the video again with the cavity analysis, and you can see that the dark spots we saw before are now colored, and you can see that the colors indicate different sizes. So everything that's blue or violet is small cavities, and red is very large cavities. So the computer tomograph measures the difference in density of the materials, so inhomogeneities can be evaluated. An algorithm will then calculate the cavities, and the exact size and position of each cavity or crack can be detected. And apart from these meteorological measurements, we can also do statistics, so there really is no limit. So we have different materials, and materials with a higher density will be visible. In this case, this is a metal component with cavities of lower densities. And this is another example. Of course, we cannot only evaluate our metal printer components, but we can also evaluate the plastic components from the plastic printer. This is the example of our crumple bag. This is a part that is plastic printed. This is actually reverse engineering, because we took an actual bag which we crumpled and then digitalized. We use different manipulation programs in order to increase wall thickness and create a CAD model. It was then minimized because the actual bag was a little larger than what we have here, and then it was digitalized and printed by our plastic printer. And here you can see a actual target comparison where we can see the comparison between the CAD model and the actual printed part. The dark blue areas indicate that there is not enough material, and everything that's in red indicates excess material. And this shows us very well if the printer prints well or not, or if there is any excess material. And different optical imaging processes can be used for non-destructive testing, for example, to check if the functions of a component are right. And it's interesting for us to see if there are any cracks, for example, in areas that we cannot see. And the component can be tested 100%. And with the plastic printers, we can also see the printing process very well. So here you can see that the layers were printed crosswise, and we can see very well how the printer worked and whether or not this is as required. And now to conclude, I have brought along the closed loop from Advanced Technology. Here we have a specific closed loop process. As I said, the client will approach us with an idea, and then we can print a prototype. So the prototype we can scan it and do reverse engineering. As I said, we use phantom freeform for that. It's interesting, for example, if we have an existing bottle crate and we see that there's something wrong in an area, we can do some optimizations in certain areas and then do reverse engineering. And for reverse engineering, we use the software Geomagic Wrap. And once the component is complies with the client's requirements, it will be constructed and after the CAD design. And this will be interesting for many of you who don't work in mold making, because this shows what such a mold actually looks like. It is an animation of what it looks like and how it works. So at the end, again, there's industrial computed tomography. I've brought along this video here with the cavity analysis of the finished component. Here again you can see the entire component. We scan it from the top to the bottom. You can see that there are some cavities in the handle areas, but the rest of the crate looks rather good. And of course we can use the computed tomograph in other steps of the process as well. We can do an actual target comparison. We compare it to the CAD simulation. We can compare the finished product with the simulation. We can compare the 3D prints. You know, we can do all sorts of comparisons. Of course, we can also compare two different components. It's also possible to measure a component with computed tomography, and after the mold has been used for 1 year and is returned to us for routine maintenance after 1 year, we will print a new part and then compare the measurements and see if there is any wear and tear. And on the right hand side you can see the finished component. And just to give you the whole picture of our advanced technology, I'd just briefly like to present the GOM ATUS 3TS scanner for you. This is an additional optical measuring tool we use. It is used particularly for components that are too large for the computed tomograph. Our computed tomograph can only measure components of sizes up to 120 centimeters and a weight up to 100 kilograms. Everything else, unfortunately, is too large or too heavy, and that's when our GOM scanner is used. We can measure components of 40 millimeters to 10 meters with this, with a high accuracy of 0.02 millimeters. For the evaluation, we use the GOM Inspect Suite 2021 software. The GOM also allows us to do photogrammetry measuring, which allows us to project the color of the CAD model. Now, before I thank you for listening, I'd like to point out that all of the things I just presented to you, so that's 3D printing, laser tech, computed tomography, and also the GOM, these are services that we offer as external services. You can see the contact details of Gerald Zimmer here, and if you're interested in these services, please feel free to contact him at any time. Please feel free to take a screenshot of his contact details. And if you have any technical questions, any questions on computer tomography or on the measuring technology at HAIDLMAIR or on today's presentation, please feel free to contact me at any time. You can also see my email address on this slide. Yeah, thank you very much for listening, and I'm looking forward to your questions. Thank you for this exciting presentation. Personally, I really liked the crumpled bag. Now let me see if we have any questions yet. No, there are no questions yet. Maybe it just takes a little. I'd like to seize the opportunity and ask a question myself. In your presentation, you said that you can combine lighter and heavier materials with additive manufacturing. Now, I'd like to know whether or not in those areas where the materials connect, there are more defects. Well, when we print two different types of materials with our laser tech, we can see that in the computer tomograph, because usually there's a difference in density. But we don't usually have defects. The components I presented in my presentation was one of our earliest components where the settings were not yet 100% perfect. So that's why we still had some defects. But by now we hardly ever have any defects in our components. Okay, now I can see that there are actually some questions coming in. What exactly is MoldMax? And why is it such a good idea to replace it by hybrid manufacturing? Well, MoldMax is a special material alloy that contains beryllium, and in Europe, many people who work in mold making don't want to use it anymore because of that. And with the hybrid technology, laser tech, we can print different types of materials simultaneously. So we can replace this alloy by a special mix of materials. Okay, thank you. And then there's another question about the material. Do you also print OTEM 9085 on Fortnite? This is interesting for fire protection components. Well, this question is difficult to answer because we can use many different materials, and this always depends on the component geometry and the nozzle size, etc. So if you're thinking about a special application here, please send me an email. We use an aliconer in our company. This is a measuring device for surface determination, and we can determine the right surface roughness here. And another question, do you have experience with 3D cooling channels when 3D printing in the molds? Yes, again, this is about our laser tech. With this hybrid technology, with the step-by-step process where we print, mill, as I said, we can realize very specific cooling solutions, and we actually do that. And this becomes especially interesting if we want to have a cooling optimized printing process and therefore use different types of materials. Okay, I think that's all the questions. Again, thank you very much for this interesting presentation, and thank you for to everybody who participated. If you missed our previous webinars or you would want to see them again, you can follow this link. We looked at different topics such as aerospace technology, ceramics, turbo machines, process phenomena, and today's webinar on mold making. So if you're interested, please register and you will then get the link. So, I would now like to say goodbye. I wish you all the best, and I look forward to seeing you again, maybe at the Form Next or a different event. All the best, take care, and goodbye.